Now that we've looked at circuits a little bit, it's time to spend a little bit more time on current, and specifically something that we'll be using, which is conventional current. So years ago, when they started looking at circuits, the scientists didn't really understand what was going on in the circuit, and they didn't really know that it was the electrons that was moving around. They thought there were particles moving, but they weren't sure which ones it was, and from their tests they actually found that it was the actual positive particles moving around in this wire. Now we know that's not the case. We know that protons are stuck in the nucleus and they're not going to be going anywhere, and it's the electrons that will be moving along. So when there is current, we know that what actually happens are the electrons are going from the negative to the positive, because it's the electrons that flow, not the positive charges. But at that time they thought it was positive charges, and so they set up some rules, and then they wrote some books and taught some courses, and then came up with more rules, more books, more courses, and before they knew it, before they figured it out, a lot had been done on conventional current. And so a lot of rules that we use are actually built on this old way, this old convention of doing things, this conventional current. And it seems a bit backwards to teach something that sort of is out of date, but it'll make your life easier, because when we come up to things like right-hand rules and so on, it'll just help to understand the difference. So what you need to do is follow this idea of conventional current, that current travels from positive to negative. So when we work on conventional current, it's positive to negative. But always know that in the back of your mind, protons don't move in the circuit. It's the electrons. So the actual flow are the electrons that's moving. So if I ever ask you what is the direction of the electrons, what is the electron flow, you know that electrons flow from negative to positive. But when we draw out our circuits, when we calculate things, and when we get to electromagnetism, you're going to just use this idea of conventional current, positive to negative. Now, as far as circuits go, when we go to a light switch and we turn on a light switch, it's pretty much instantaneous. You flick the light switch, even if your light bulb is quite a distance away, the light goes on right away. And so that usually leads students to think that when you flick the light switch, the most common answer I hear is that the electrons are traveling at the speed of light, because after all, you do flip a switch, light's really far away, it seems to be instantaneous. So that's not an unreasonable thing to come up with. Sure, there'll be some resistance, so speed of light might be pushing it, but awfully fast. But when we actually look at it, it's not the case. And there's an example in your notes, and you can take a look at it in your notes. But what the example does is it looks at some wire, and so we make some assumptions, and we say we have a certain thickness of the wire and a certain length, and we'll say this wire is made out of silver, just because it's a little bit easier to look at silver. So we figure out how much mass of wire this would be, and how many electrons we'd have in a certain mass of wire, and we work our way through towards the drift velocity. Now you don't have to memorize or know very closely the derivation and how we got about this, but what I do want you to know is that it's a very small number. Okay. When we look at drift velocity, and drift velocity is a term that we use for the actual speed of the electrons in the wire. When you turn on the switch and the current starts to flow, the drift velocity is actually quite slow. Well, at least to me and you. In the scale of an electron, it probably is moving quite quickly, but for us, it seems quite slow. In fact, that if you flip the switch, not only would it not turn on right away, you have to wait a long time before the light actually comes on. So what's going on? Why does the light turn on right away? And for this, we want to think of the idea of electric fields that we did in the last unit. And there are electric fields set up. So if we have, say, a positive and a negative area, then as soon as you turn on, as soon as you make a connection to your switch, an electric field turns on. And this electric field takes whatever charge is moving, whatever charge is present, and moves it along. And so if you imagine a wire, and the wire is full of electrons, as soon as the electric field is on, it causes all the electrons to move right away. And so one example I often mention is, imagine that you have a pipe that's like 200 meters long, and this pipe is filled with ping pong balls, and you have someone on the other side waiting for the ping pong balls to come out. Well, if you push in a ping pong ball, instantly you get another ping pong ball at the other side. Now that's not what's happening in a wire. The electrons are pushing one another, but that is a little bit what it looks like. As soon as the electric field comes on, there's the flow happening, and then we get current right away. When we did our unit on mechanical energy and conservation of energy and power, one of the formulas that we worked on was the power was the amount of work done over time, or change in potential energy, or change in energy over time. This power was measured in watts. Well, power is also applicable to circuits. However, the formula for power starts with this one: power equals VI. And power equals VI is, we have power in watts, we have voltage measured in volts, and then currents in amperes. So if we, for example, wanted to find out what is the power used by a CD player, then we have a 6-volt CD player times a current of 0.450 amps. Remember always to use SI units. And so we get 2.7 watts of power. Now, although this is the formula for power, we can actually create a few runoff formulas from that. If we combine power with Ohm's law, with V equals IR, and do some substitution, then we get a few other formulas for power, or two more. We can get power is V squared over R, and we can also get power equals I squared R. So that really leaves us with three formulas for power. Now, as long as you know power equals V times I, and you remember Ohm's law, which is extremely important, then you can easily get the other two formulas. Just a bit of a side note, whenever you're looking for power dissipated or power loss, I find that starting with this formula here, P equals I squared R, is usually your best bet. And so if the question comes up, was the power dissipated in the light bulb or something like that, try I squared R first. It just tends to work out easier. So now if we have an example here, what are the resistance and current through a 60-watt light bulb is connected to its proper source of 120 volts, and how about a 100-watt light bulb? So we start with resistance. It's going to be P squared over P, and so that's going to be 120 volts squared over 60 watts. So that gives us 240 ohms. And if I'm looking for current, then current I can use Ohm's law of V over R, where my voltage is 120 volts, and my resistance is 240 ohms, and so that gives me a current of 0.5 amperes. Now if we have a 100-watt light bulb, we do it much the same. So my resistance will be 120 volts squared divided by 100. So that's 144 ohms. And now if I look for current, current is going to be V over R 120 divided by 144 ohms, and it's a current of 0.833